Hello?
Hello?
Yes, hello?
Yes, this is Mr. John Video from YouTube.
Sorry, you said John Video?
Yes, sir, that's right. I'm calling to tell you your channel is terrible and you need to take it down.
Take it down?
Your channel stinks and you need to take it down.
Oh, well, I'm sorry to hear that. I'd love to have a chance to at least plead my case. Could I get your email so I could provide some kind of written response?
Come up with something.
Yeah, that's gonna be Joe Video at youtube.com
Okay.
.org at www.
Is this Jasper?
Look, don't feel you need to answer. I know it's you.
I don't know where you guys have been, but things here just aren't the same without you. This morning I had to drink my coffee out of a candle holder. I know things have been tough.
During times like these, no one knows when it'll all be over, and that can lead people to do some pretty strange things.
You know, one minute you're a perfectly rational human being, and the next you're inventing ridiculous fictional narratives and making up cartoon regional accents for your inanimate household objects. And look, it could happen to any of us.
But if there's one thing I know, it's that family will take us through anything.
And when we've put all this behind us, we can look back and smile.
Knowing that we did everything we could to keep that family together.
You know what I mean?
Did you hear what he said? Yeah, I heard.
So again, you don't have to answer.
Just know that whenever you're ready, you have a place here. Oh, and Jasper,
Yeah, boss?
don't ask me how I know what your voice sounds like, even though I've technically never heard you talk out loud before. It's probably best not to spend too much time picking that one apart. Now, be careful out there, you two crazy kids.
You really mean it? We can come back if we want to?
You got it, dude. Good morning, guys. So today we're going to be looking at something that is an extension of what we worked with yesterday, of learning how to simplify these radicals so that we can put them in forms that allows us to do more complex things with them. And what I want to say before anything else is that if you had any problems with yesterday's work, that's okay. I want you to think of the rest of this week as a reinforcement of two concepts. One, the basics of simplifying that we worked on yesterday. And then today, how we can add and subtract radicals once we've simplified them. So tomorrow's homework, you're going to see is really just a combination of the two. The video is really just going to review tomorrow some examples of each so that by the end of the week you can reinforce it. So once again, look forward to a quiz over this material on Tuesday of next week. So the simplest way that I can think of to describe this is that you want to connect two ideas in your head. The first is the working knowledge you needed to have yesterday of perfect squares and cubes, because knowing those and being able to kind of pry those out, that's what's going to allow you to be successful in simplifying and adding and subtracting these things. And the second thing is a really old idea, combining like terms, especially when we're dealing with variables. So you guys probably remember that if I have like an 8x squared and a 2x, I can't add those two things together because they're not like terms. This works very similarly. Now, if it was an 8x squared and a 2x squared, then I could easily combine those and add them to form 10x squared. If you get that idea, you've got everything you need for this. Only in this version, instead of a variable, I want you to think of the radical, or what we would really technically call the radicand itself. So in this first example, we're in good shape because we've got two, in a sense, like terms. They have like radicands. We have a single square root of 10 here, and we're subtracting 6 times the square root of 10 from it. So we would just combine these like terms like we would in any other case. So we have a positive 1 of these and a negative 6 of these. And so we're going to combine them to get negative 5 times the square root of 10. Take a minute and pause the video. If that kind of went over your head, just understand, just like when we were combining like terms with variables, we can do the exact same thing with radicals. But those radicands have to be the same, just like they do with variables. So take a look at this second example. We've got the cube root of 7 plus the cube root of 7 minus 4 times the cube root of 5. Now, first off, if you're thinking to yourself, I can't combine all three of these things, you'd be absolutely right. So take a second and think about why you might not be able to do that. Over and above that, think about what you can do. Well, hopefully when you look, you see that we have two alike radicands here, 1 cube root of 7 and 1 cube root of 7. So we can add those two together and get 2 times the cube root of 7 minus 4 times the cube root of 5. Now, what can we do with the rest of this? The answer is we can't do anything with the rest of this. It has been subtracted, it has been simplified as much as it can. Now a little bit more of a curveball here. Now, at first glance, it looks like we can't do anything with that because they're not like radicands. This is where remembering your perfect squares and your perfect cubes comes in really handy. As you look at each one of these, think to yourself, are there any perfect squares, since these are square root signs, that I can pull out of these? So what factors multiply to equal 12? And are any of them perfect squares? What factors multiply to equal 75? And are any of those perfect squares? That's where remembering those perfect squares comes in so handy. Remember 1, 4, 9, 16, 25. And in just those 5, we've already hit the key to this. So I know that 12 is equal to 4 times 3. So I'm going to write that like this. And I know that 75 is 25 times 3. So I'm going to write that like this. Now you know you're on the right track if when you break these down into their factors, you see a common factor in each one. That's going to let you know you're kind of heading in the right direction. All right, so let's take the square roots that we can. We can take the square root of 4, that's 2. We bring that out and multiply that by the 7, and that gives us 14 times the square root of 3. And we can also take the square root of 25. We know that that's 5, so we bring that out. And now we're in a much better position. We have like terms, if you want to think of it that way. 2 square roots of 3 that are each being multiplied by a different factor. So now we can just combine them through subtraction. So 14 times the square root of 3 minus 5 times the square root of 3 gives us 9 times the square root of 3. I'm going to show you another couple of examples that you'll see on today's work, but I'm going to dissolve real quick before we do that. So I'll be back in just 1 second. Now, back again. You're probably noticing the big difference here is that we've added variables into the mix. And I have a feeling that for some of you that might have been tricky on yesterday's homework. So remember, it's fairly easy to take the root of a variable as long as we can find an exponent that works for what we need. So this first part, for example, the square root of x squared, that's pretty simple. Well, the square root of x squared is x, so we're just going to write that as 2x. And you might feel like you're in just as easy shape over here, but take a look at the problem. We have the square root of x to the 5th, and we have it twice. Well, we can't take the square root of x to the 5th, because since we don't have an even exponent, we can't split it in half, which remember is essentially what we do here. But that doesn't mean we're stuck. Remember, just like with constants, we can break variables into factors that allow us to make better sense of this. So if you're already thinking right now, okay, square root of 25, I know there's going to be a 5 on the outside of this somewhere, you'd be absolutely right. But I'm going to show you a maybe more efficient way of doing that. Watch what I'm going to do here. I left the 25 alone. I combined it, if you will, or joined it with an x to the 4th. That was 4 of the x to the 5th, if you will. And then I'm going to multiply it by the remaining x. Just stick with me for a second. I'm going to do the exact same thing over here. Now, remember, you know you're on the right track if you're isolating radicands that you know are going to be left, because you can combine those in the end. Well, can I take the square root of 25x to the 4th? Sure I can. I'm going to bring this down. The square root of 25 is 5. The square root of x to the 4th is x squared. And then inside, I'm just left with that square root of x. But that's okay, because watch what happens over here. Square root of x to the 4th is x squared. And I'm left with that square root of x on the inside. Hey, good news. Now, even though I can't do anything with this, I've got some like terms I can combine over here. So I've got a 5x squared times the square root of x plus one more x squared times the square root of x. So negative 5 plus positive 1 is going to leave me with negative 4x squared times the square root of x. We can do the exact same thing with cube roots. And I'm going to let you know that on quizzes, especially since we're so far from one another, I'm going to keep a basic distance on that, but let's look at one anyway. So if you look at this over here, we've got 4 times the cube root of 81 times x to the 6th minus the cube root of 24 times x to the 6th. Now I'm going to tell you right now, 81 is not a perfect cube, 24 is not a perfect cube, there's no single factor. But again, remember your cubes. What's 1 times 1 times 1? 1. 2 times 2 times 2, 8. 3 times 3 times 3, 27. So on and so forth. So this will allow us to kind of break these down, and we can think, oh, okay, maybe I can break this up into factors that I can work with. So let's do that with this first one. So I think about this for a second, and I think, okay, 27 times 3 is 81, and 27 is a perfect cube. So I can work with that. Think for a second. Why did I leave x to the 6th over here? Well, because the cube root of x to the 6th is easy to do, because the exponents allow it. Just divide that 6 by 3. So x squared times x squared times x squared is x to the 6th. What does that leave us over here? A 3. And let's do the same thing with the other one. Well, are there any factors of 24 that are perfect cubes? And the good news is 24 is a relatively small number, so we don't have that far to go. I can think 12 and 2, no. I can think 24 and 1, no. But when I get to 8 and 3, 8 is a perfect cube. So watch, I'm going to do the exact same thing here. 8x to the 6th times 3. Once again, good news. Since I see a 3 here and a 3 here, I know I'm probably on the right track. So let's bring everything out. Now don't forget this 4. We're going to have to multiply it through. So what is the cube root of 27? 3 times 3 times 3 is 27. So that's going to bring a 3 out. And then x to the 6th, the cube root of that is x squared. So 4 times 3 gives me 12x squared. Still left with that cube root of 3 on the inside. Can't do anything with that. Same thing over here. Cube root of 8 is 2. 2 times 2 times 2 is 8. Same thing with our x squared. And then we've still got the cube root of 3 on the inside. And now we can combine these terms. Same radicand. Square root of 3, square root of 3. So we just combine them. 12x squared times this minus 2x squared times this leaves us with 10x squared times the square root of 3. Now, I want you to go back and watch this a couple times if it's tricky for you. In addition, e-text, supplemental videos, all of that matters. Remember, tomorrow's work is going to review what we've done over the last few days, because we're looking again at a quiz on Tuesday. So if you watch this video early enough in the morning and you want to come on live conferences, be my guest. You can also email me directly. Friday's work, tomorrow's work, We'll review all of this material, and then you'll have time to see me at conferences next Tuesday before the quiz as well. Good luck with this. Take it slow. Remember 2 things. We have to combine like terms, which means our radicands need to be the same or else we can't go anywhere. And you need to know your perfect squares and perfect cubes. If you have both of those things, you should be fine. I want to wish you a very good day, and I will see you tomorrow.